the enigma of Earth's first megacontinent. Doug Ettinger's article challenges mainstream paradigms about the first, unique, and random distribution of raised continental crusts on the Earth's surface. Their creation is a mystery, but can be resolved by the following hypothesis. Why does Earth possess megacontinents with active plate tectonics? No other celestial body possesses such an amazing feature. A good starting point is to develop a hypothesis of how such a raised landmass that only covers 1/4 of the globe's surface above sea level can develop in the first place. I suggest that the proper approach is to formulate a theory for the first appearance of a megacontinent before attempting to answer the more detailed and complex positionings of its parts over time, which is a popular approach among geologists today. By starting from scratch at the beginning, science can better answer other associated mysteries. Why do megacontinents amalgamate and disperse in an episodic nature? Why do they migrate both latitudinally and longitudinally, moving between hemispheres? Why is each broken piece of this megacontinent currently surrounded by plate boundaries whose interior portion is composed of ancient crystalline rock called cratons? Why are these continental crusts thicker and composed mostly of granitic rock, while the oceanic crust is basaltic? This paper postulates that a huge icy impactor struck and penetrated the early Earth's very hot molten mantle, causing a giant crater with its expelled and oozing material to cover about 1/4 of the existing young protocrust. The mixture of mantle materials of the two bodies caused a different granitic crust from the original, forming oceanic basaltic crust, which still exists today. The raised mass above the average surface elevation caused an initial imbalance that began the higher continental surface crust to start shifting or drifting laterally on the spinning planet's surface. This movement had the aid of added volatiles rising from the deeply impregnated, melted impactor. As the pool of molten lava inside the crater eventually cooled and crystallized, the continued unbalanced condition would eventually split apart this proto-megacontinent to establish what is known today as continental drift. Mature plate tectonics would start much later, when there was time for more cooling to increase the hardness and thickness of the different crusts, so that the heavier oceanic crust could dive under and push up the interfacing continental crust to create volcanism and mountain chains. This radical new hypothesis differs from the present consensus of NASA's giant impact theory. This new version of impact did not create the moon, but produced the first megacontinent from a global mixture of mantle material from both the Earth and its impactor. This new impact version explains Earth's orbital displacement sunward until it found a new orbit that slowly caused the Moon and Earth to share, in a gravitational manner, the same orbit. Many other mysteries can be resolved, such as Earth's liquid water, plate tectonics, continental drift, geological hotspots causing island chains, the formation of intrusive granite not reproduced in the rock cycle, the reason for separated basaltic oceanic crust and continental granitic crust, the slippery moho discontinuity, and the great unconformity caused by tectonic plates not completely cooled and differentiated, due to this new version of a penetrating impact of global scale. Resolution of the above conundrums requires an understanding of some basic geological diagrams that are presented. Please take a glimpse of number 1, the Earth's cross-section and structure. Number 2, the ideas for plate tectonics. Number 3, the plate tectonic boundaries surrounding the continents. And number 4, the cratons of the oldest rocks remaining on each subcontinent after the first megacontinent broke apart, wasted away, and reassembled several times. Why Earth's landmasses do not eventually erode below sea level over time. Many plateaus form as magma deep inside the Earth pushes toward the surface but fails to break through the crust. Instead, the magma slowly lifts the large, flat, impenetrable rock above it. The debated forces are thought to cause uplift by the slow collision of tectonic plates that are still lifting areas such as the Colorado Plateau. The author believes other, more important forces give power and strength to the lithosphere's motions to cause the uplift of plateaus and mountain ranges. There are approximately 34 major plateaus in the world that have rich deposits of minerals, indicating the ongoing mixing of the Earth's crust through plate tectonic processes. Plateaus occur on every continent, take up a third of the Earth's land, and change with the process of erosion and mass wasting. Weather and drainage systems change the plateau's surface, including the cutting of valleys by rivers. Also, the melting of ice sheets on land through the ages creates powerful subsurface rivers that make fjords and continental shelf canyons. Eventually, plateaus and mountain ranges should all be worn down to sea level over millions of years. However, the continuance of continental drift causes the moving lithosphere to pile on top of existing landforms or dive beneath the landforms, creating episodic plateaus and mountain ranges. This continuance is caused by the original imbalance of the first impact crater, or megacontinent, that keeps hunting for a tenable equilibrium of masses on the spinning planetary surface. Plains form in different ways. The process of the layers of rock can form both on land and under the sea, which is then uplifted above sea level. Some plains form as ice and water erode or wear away the dirt and rock from higher elevations. Water and ice carry rubble, rock, and other material called sediment down hillsides to be deposited elsewhere. As layer upon layer of this sediment is laid down, plains form. As the layers become thicker and deeper, sedimentary rock forms. The displacement of materials by erosion continues to change isostatic forces that cause either upward or downward movement of the crust. This constant motion of material diving to deep depths is called the rock cycle, which initially turns from sedimentary rock to metamorphic rock to molten rock, finally becoming igneous, and then repeating the cycle via more mass wasting of the continents. However, the deep, small-grained intrusive granite is never part of the rock cycle. This type of granite can only be created by a high-energy penetrating impact that can never be recreated solely by processes created on Earth. This dilemma is called the granite problem. The study of landforms on other planets and moons. Do other celestial bodies share the same surface features and cross-sectional properties as Earth? The answer is no. Earth is extremely unique in having two different surfaces, one that is solid and rocky, and the other that is liquid water. Diversity in life occurs because of this grand scheme, and our continental landmasses that originated from an ancient megacontinent made this possible. How did this enigma occur? Let's examine the other celestial bodies for similarities and differences. Their study may lead us to develop and corroborate a theory about Earth's megacontinents. Astrophysicists have imagined interesting theories for enigmas about the other rocky planets and moons, mostly collisions, including our very own planet. Space-age data reveals a similar cross-section for all the terrestrial planets and the explored major moons. They all have high-density cores with differentiated outer layers of lighter metals and volatiles. Many cores are hot and molten, producing magnetic fields due to induced convective electrical currents of molten liquid and their rotation of the entire body. The lightest volatiles of gases are eventually emitted from the surface to become atmospheres or freeze as solids if the gravity field is strong enough to hold them. If the atmosphere is deep enough, its pressure can turn water vapor into liquid oceans, such as only occur on Earth. A safe assumption is that all these bodies started as a molten globe of a homogeneous mixture of elements and compounds that began orbiting the Sun at various distances. This chemical separation by partial melting and outgassing of volatiles is called geological differentiation for any planetoid. As the planetoid's interior differentiates, less dense liquids rise from the melt toward the surface and crystallize to form a crust as they are cooled. Inductive reasoning shows this to be true by observing how a blast furnace works. The so-called impurities, or slag, rise to the surface of the molten bath, while the separated denser iron underneath is poured into ingots. A chemical periodic chart shows what lighter materials should be found in a planetoid's crust and atmosphere. These materials are in the first 3 rows of elements, with atomic numbers less than 20, with the more prolific being hydrogen, carbon, nitrogen, oxygen, aluminum, silicon, and sulfur, which make up the most abundant compounds in the solar system. Water, ammonia, methane, nitrogen dioxide, silicon dioxide, and carbon dioxide. The heavier metals greater than atomic number 20 are found in the cores and deeper in the mantles of planetoids, such as titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. What we discover on Earth and the other hard celestial bodies is indeed this differentiation described above. But why does Earth have this agglomeration of lighter elements and compounds found on about 1/4 of its unusually elevated surfaces of the globe, called continents? The initial separation of the different constituents of planetary materials should result in the formation of distinct and evenly compositional layers globally. Could an immense collision on Earth with another celestial body be the reason? Let us examine how astrophysicists try to answer anomalous conditions found on the rocky terrestrial planets and major moons. The answers are generally collisions with smaller bodies and should offer a clue to what happened on Earth. The study of Mercury's surface. The first case is Mercury, which is much smaller than Earth, but almost as dense. Mercury's density can be used to determine the details of its inner structure. Hence, its core must be larger and richer in iron, occupying 55% of its volume, while for Earth, this proportion is 17%. Mercury may have been struck by a planetesimal of about 1/6 that of its original mass, which stripped away much of its outer silicate mantle, leaving behind mostly core materials. Another likely theory is that as the proto-sun contracted, temperatures at Mercury's orbit could have reached 2,500 to 3,500 Kelvin or higher, thus vaporizing the mantle, which was carried away by the solar wind. Neither theory produces two distinct, dissimilar surface elevations and compositions, such as are present on Earth. However, similar collisional and vaporizing theories are used for Earth. Let's now move to Venus, the next planet away from the Sun. The study of Venus's surface. Again, astrophysicists use a collision model early in the planet's history to explain its retrograde rotation, unlike any other planet. This model includes moon making. Venusian moons gradually spiraled inward and crashed due to a strong solar tide, causing Venus to be moonless. Venus has no elevated surfaces comparable to Earth, except for numerous volcanic mountains, situated on a surface covered with 80% volcanic plains. Earth's crust is in continuous motion, but without plate tectonics, Venus's crust cannot move to dissipate heat from its mantle. Hence, the mantle heats to critical levels, causing cyclic volcanism that recycles the crust every 600 million years, creating a much older crust than on Earth. The reasoning is that with the lack of water, Venus's crust is too stiff or viscous to allow plate tectonics. However, one cannot forget that Earth has megacontinents that drift and subduct to recycle the crust. Venus has no such mechanism, thereby leaving only outgassing and volcanism to form its surface, which should be normally expected for any hard, dry, spherical celestial body in the solar system. Venus's dense atmosphere is composed of 96.5% carbon dioxide and 3.5% nitrogen. Its atmosphere is depleted of radiogenic argon, a marker of mantle degassing, which suggests an early end of major magmatism. Evidence of no water is probably due to atmospheric erosion during the first billion years by the solar wind that occurred during the Sun's T Tauri phase. This T Tauri phase likely afflicted the atmosphere of all the terrestrial planets, assuming that Earth was originally at 1 astronomical unit. If Earth were at 2.7 astronomical units as is proposed, then during the T Tauri phase, its pristine atmospheric gases would be retained. The differences in atmosphere between Venus and Earth are striking. Inductive reasoning leads to Venus's lack of continental drifting and plate tectonics, which can create a sink for removing carbon dioxide. Also, the lack of nitrogen probably means its meager production was boiled off due to its closeness to the early Sun. The study of Mars's surface. Mars is the best explored celestial body outside of the Moon. Its cross-section is like Earth, having a basaltic rock crust like Earth's oceanic crust. Mars has a differentiated dense metallic core consisting primarily of iron, nickel, and sulfur. The silicate mantle formed many tectonic and volcanic features. Alternatively, these features may have been created by high-energy electromagnetic plasma discharges, having many similarities to an electric arc welding process. The crust and mantle are now dormant with no global magnetic field. the surface was subjected to the late heavy bombardment, with impacts from that era shown on 60% of its area. Martian paleomagnetism is like alternating bands found on Earth's ocean floors, with no clear origin. Possibly, a planetary dynamo ceased to function after about 4 billion years. But magnetic reversals are a true mystery on whatever planet they are found. The very thin atmosphere of mostly carbon dioxide cannot support any liquid water. Some water may be retained in frozen underground reservoirs. The atmosphere is lacking in nitrogen at only 1.89%. What happened to the nitrogen? Perhaps most of Earth's nitrogen was delivered by its icy impactor, which did not occur for any Martian impactor. Mars cannot escape, having its very own predicted immense impact in the northern hemisphere, shown in blue on an elevation map. Theory suggests that Mars was struck by a Pluto-sized body about 4 billion years ago and causing the hemispheric dichotomy. However, this dichotomy exhibits no plate tectonic movement and is only about an average of 6 kilometers or 3.7 miles difference in average elevation, unlike 29 kilometers, 12 miles for Earth. Why did such a huge impact leave the Martian crust in the highlands uncracked and not generate a rim-like structure centered on the point of impact? And this prediction should lead to the thinking that Earth had a similar collision. Study of Ganymede's structure. Ganymede, Jupiter's largest moon and most massive moon in the solar system, is a unique body for study. An interesting fact is the theory that this moon contains more water than Earth's oceans combined. Ganymede, like the Earth, has a liquid iron core with a high electrical conductivity that, via convection, creates a magnetic field. About a third of the surface is saturated with impact craters and dated to about 4 billion years ago, roughly the time of the late heavy impact period. The moon is thought to be fully differentiated, with an iron sulfide iron core, a silicate mantle, and outer layers of water ice and liquid water, not unlike the Earth's with its outer liquid water ocean. Ganymede's very low moment of inertia determines its substantial water content and fully differentiated interior, with the stacking of several ocean layers separated by different phases of ice due to an extreme depth of about 800 kilometers. Ganymede's special crystalline phase structures and its silicate mantle may have been like Earth's impactor and played a large part in producing the mysterious granitic structures found deep in Earth's crust and the lighter granitic continental crust. Earth's impactor hypothesis that occurred at 2.7 astronomical units uses a body like Ganymede as a model for the impactor. Such a body may very likely have more water, ammonia, and other lighter volatiles that could be delivered to Earth. This frozen hard sphere could enable penetration into the Earth's young, soft molten mantle to buffer the complete destruction of the two bodies. The above study of these celestial bodies, through inductive reasoning, leads to an interesting, tantalizing hypothesis. Number 1. All these bodies show an impact history, occurring about 4 billion years ago, including the Earth and Moon. This impact event is called the Late Heavy Bombardment, or LHB. The proposed hypothesis is that Earth was struck by an impactor the size of Ganymede that created the dispersal of rocky debris throughout the inner solar system. The main belt of asteroids at 2.7 astronomical units was also produced at this time by this collision. These asteroids are comparable to smashed and/or melted crustal material from planetary surfaces. The age of the oldest cratons on Earth corroborates this event, since their plutonic rock was created by the collision at about the same time. Number 2. This new version of an impactor theory creates a global crater after the impactor gouges the Earth's crust and mantle. This crater oozes outward, a mixture of molten materials from both the Earth and the impactor, to create the first elevated landmass or megacontinent that produces different rock from its original oceanic crust. Number 3. The tremendous kinetic energy of impact displaced the Earth's orbit sunward until it sought a new orbit close to the existing terrestrial planet now called the Moon. This new impactor version created the mysterious Earth-Moon system and answers its special capture mode. Number 4. The geology of the top layers for the inner planets shows significant plate tectonic and continental drift formation only for Earth. Only Earth shows major elevation differences in the terrain, except for volcanic mountains on the other celestial bodies. Number 5. All inner solar system bodies have produced theories about major collisions, including NASA's giant impact hypothesis for the Earth and Moon. Mars has the theory of impact that created the largest volcanic plain in the solar system, yet it survived the incredible kinetic energy of an impact. So, major impacts should always be within the range of choices and never be ruled out in addressing anomalous conditions. Number 6. Intrusive, smaller-grained, granitic-type rocks have yet to be discovered by any space probes. This type of granite rock is found only on Earth and is proposed to have come from the deep infusion of volatile materials into Earth's mantle by an impactor. Number 7. Only Earth demonstrates a preponderance of nitrogen in its atmosphere. The thought is that the impactor's ices brought ammonia and nitric and/or nitrous oxides that converted to nitrogen as one of its products of reduction to become a stable element for Earth's atmosphere. Number 8. Only a huge raised and filled impact basin on Earth can address the cause of an ancient megacontinent that dates to 3.9 billion years ago, closely aligning its creation with the late heavy bombardment LHB. I implore anybody to step forward and provide another plausible reason for a megacontinent's birth. The proposed reason should explain several geological phenomena, including plate tectonics, continental drift, the Moho layer, geological hotspots, crustal composition differences, small-grained intrusive granite formation, early glaciation, the Great Unconformity, and atmospheric nitrogen, as does the given proposal. The Apollo mission findings do not support NASA's giant impact hypothesis. This story needs replacement by another type of collision that adds a plausible capture mode for the Moon and the creation of the first megacontinent. With so many ideas swirling around, NASA is having difficulty sorting out the correct proposal for the formation of the Earth-Moon system. NASA is dealing with paradigms that strongly resist changes in their thinking. The worldviews underlying the theories and methodology of astrophysics and planetary science are deeply entrenched. These paradigms are: A. The Moon was never a planet. B. The Earth was never displaced from another orbit by collisional forces. C. The impact of a rogue minor planet making a raised and filled rimmed crater becoming a megacontinent is not imagined. D. One rogue planet could not possibly deliver more precious volatiles such as water, nitrogen, and methane to make up the ancient ocean and atmosphere. E. The origin of Earth's water cannot be due to the planets residing close to the solar system's frost line at 2.7 astronomical units during the hot T Tauri phase of protostar formation. Such paradigms should be removed. Hope emanates that the scientific community will eventually seek some version of these new ideas to understand how, from chaos, our genesis of Earth and life came to be. Strangely enough, this storyline agrees with parts of the book of Genesis in the Old Testament Bible. The creation of the firmament, with waters from above and below, could well be the first megacontinent. Returning to Earth's geology, more evidence is gathered to convince the hardcore believers of their false, ingrained paradigms about the first megacontinent, such as ridiculous plumes rising from the liquid core. Certain scientists have stared too long at lava lamps in their bedroom. The premise of an original continent forming after Earth's birth about 3.9 billion years ago by a huge impactor is compelling. This all-important megacontinent birth created the scenario for life beginnings, which requires both water and the rock cycle. Further supporting geological topics of the Great Unconformity, GU, the granite problem, the Moho layer, and random geological hotspots are all explained in the article, The Enigma of Earth's Megacontinents and Their Connections to the Evolution of Life, by Douglas Ettinger, found in ettingerjournals.com.